So, this is the next session in the continuation of what we started, solving questions of the statistical process control, and this is one of the question which is based on finding the range chart. So we will be finding the range control limits, the upper control limit and the lower control limit, and let's see how this question is being posed here. And this is the simplest case. Orange juice is dispensed into cartons with the nominal weight of 500 gram. So do not confuse your mean with the nominal weight. So if you read the first line, the first two lines of the question, orange juice is dispensed into the cartons with a nominal weight of 500 kg. And then in the second line, they are telling you the actual weight dispensed is a normal variable with the mean set at 504 grams. So this is your actual mean. So whenever you will be using, because see, when you will be finding the control limits, you would need the mean, which you refer as a x bar or maybe r bar. So that is your mean actually. So don't confuse it with 500. So your mu is 504 grams and not 500 grams. And standard deviation is 1.6 grams. So sigma is 1.6 grams. Now let's move forward and what's being asked to us. A range chart is to be set to monitor the weight of the soup dispensed. A sample of 5 canes. Now n is equals to 5. Right? Will be randomly selected from the production line every half hour. So how often are we taking our sample? Right after 30 minutes. And the only question that we've been asked is to find the control limits for the range chart. But what do I need to find the like if you refer to the first chapter of this module about statistical process control, the formula to find the control limits for the R chart, now we're talking about the control limits for R chart. What was the formula? For the UCL, it was, I believe, for the UCL, it was, let me check here. It's just for the confirmation. The formula was, I believe, yes, D4, R bar multiplied by D4. And for the lower control limit, it was R bar into D3. So these were the two formulas, right? But in the question, in the information that has been given to us, there's one thing missing, R bar, because D4 and D3 can easily be looked at from the table, statistical process table. Given that we know the sample size, our sample size is 5, so we can go to the table and we can look for the corresponding value for the D4 and D3. But the thing is, we do not know the R bar. Now, the formula to find the R bar is either you have the ranges of all your sample, you take the sum of all those ranges and divide it by the total number of samples that you took. And the other formula to find the R bar is you multiply the standard deviation with the D2, with small d2. Now, from the statistical process controls table, I need the value for the D4, I need the value for the D3, I need the value for the small d2 at n equals to 5. Now I can go back to my table. So this is our table and let's see what are the values. So I'm looking at the corresponding to the fifth row because my sample size is 5. Okay. So I need my D2. My D2 is 2.326. My D3 is 0 and my D4 is 2.114. So these are the three values that I'm looking for, right? I can take the snippet of this. Now, can you make the calculations? To find the R bar, what do I do? My standard deviation is 1.6. According to the question, 1.6 grams. Multiply, what was my D2? My D2 was point 0.2326, 2.2326. 2.326. That would give me my R bar. And my upper control limit would be, I multiply 1.6 into 2.326. I would get what? I'm getting 3.7216. 3.1, 3.7216, 3.7216. So this is my R bar and for the UCL, it would be 3.7216 multiplied by D4. My D4 is 2.112, 2.114. And my LCL would be D3 is 0. So 0 multiply by with any number would get me what? 0. So I'll get 0 here, and there would be some value for this here. And my UCL would be 7.867. 7.8867. Right. So these are your control limits for the range chart. So that is it. That is it for this question. Simple. Now let's move with this question and let's see what we can do here. Now this is a bit lengthy question, and a bakery, and I'll just solve this question because I think we have went through the concepts in the previous questions. A bakery products produces frozen pizzas for takeaway pizzas outlets. These pizzas have a nominal diameter of 30 centimeters, so don't confuse it with with your mean. This is not your mean. 30 centimeters is not your mean. They will explicitly tell you that this is your mean. So look at the second line. From historical data, the actual diameter is a normal variable with a mean of 30.2 centimeter and a standard deviation is a standard deviation of 0.6 centimeters. Now I'm going to, and my n is 4. My n is 4, a random sample of keep showing. So my n is 4. And how often I'm taking my sample? I'm taking my sample right after 2 hours. So calculate the control limits for the X bar chart. We have our mean, we have our standard deviation. So we know, and what is our mean? Mean is 30.2. So mean plus minus 3, standard deviation, and under root. So this would give me my control limits for what? This formula would give me control limits for X bar chart, or you call it X bar charts. So this would give me my formula for X bar chart. And I'm plugging in the values. I'm not doing the complete calculation. My X bar is 30.2. And for the UCL, it would be plus. And for the lower control limit, it would be minus, right? Let's should for the UCL, it would be plus 3. My standard deviation is 0.6. 0.6 divided by 4 under root. Right? And for the LCL, this would be 30.2 minus 3 into 0.6 divided by 4 under root. So that would give me my LCL. And this would give me the control limits for the X bar chart. So this is for the X bar chart. Now let's move toward finding the control limits for the range chart. How would I do for the range chart? I need the same limits for the range chart, the lower control limit and the upper control limit. What I'll do? What is the formula to find the limits for the range chart? We just did that in the previous question. I need my R bar. How would I get my R bar? Do we have any formula? Yes, exactly. Because R bar is not explicitly being given in the question statement. So I know, because I know the standard deviation and I know my sample size equals 4, using sigma equals to 0.6, standard deviation, and n equals to 4, I can go and I can basically use this formula, right? So my sigma is 0.6. My D2 would be what? If I go back to the table again, My sample size is 4, this 4. And I need my small d2. My small d2 would be 2.059. 2.059. This d2, small d2, against 4, the sample size of 4. This n stands for the sample size, right? What was the value? Again, 2.059. 2.059. So here you would got your R bar, the value for the R bar. And the R bar would be what? Can you guys calculate? The R bar would be 1.2354. 1.2354. So this is your R bar. Now you can calculate the value, the upper control limit and the lower control limit. The upper control limit would be R bar multiplied by D4, and lower control limit would be R bar multiplied by D3. You have your R bar. The value for the R bar is 1.2354. And if your sample size is 4, what would be the value for the D4? What would be the value for the D4? The D4 would be 2.282. 2.282. And here, by the way, there's a little mistake here. This is 3. For the lower control limit, it's D3, not D4. And lower control limit would be 1.2354 into 0. So this is how you will get your answer. And your upper control limit would be 2.819. 2.819. So that would be your answer for the upper control limit, and your lower control limit would be 0. Perfect. And how did I get this, the value for the D4 and D3 again? My sample size is 4. I'll go here. See, my D3 for the sample number 4. This is your sample number 4. Corresponding to this value, your D3 is 0. Your D4 is 2.282. I hope this makes sense. 2.82, and this was your D3. Perfect. Now move towards the C part. What is our C part? Calculate the probability of the false signal. On the X bar chart, we are finding the false signal on the X bar chart. What do we mean by false signal? What do we mean by false signal? And what do we actually mean by signal? Signal is the process when it tells us that our sample mean is out of control, is either above the upper control limit or below the lower control limit. So that's what we mean by signal. And sometimes what happens is, because we as a human, and because this is a statistical process control, and there's always a margin of mistake, a margin of error. Sometimes what happens is, what we pick as our sample, as a random sample, that can sometimes mislead us in two different directions. Uh, and the most obvious one is the type 1 error. The false signal is also referred as type 1 error. And what do we mean by false signal? Type 1 error. It means that when our complete whole process was actually right, was actually fine, or you would say in control, but the sample that you took, the samples tells the different story. And what is our different story in this context? The different story is that it says that your process is out of control. So sometimes this happens. Our process, our complete process, our machine was perfectly working. It was fine. It was in control. But the sample that we took, the mean for that particular sample happens to be either like out of the limits, either above upper control limit or below lower control limit. So this is basically the we refer it as a false signal, and there's always a chance of a false signal, because again we are talking about we're learning statistics, we are talking about chances, we are talking about probability, right? So there's always, although we try to minimize the probability, our objective is to minimize the probability of wrongdoing, and maximizing the probability of like being perfect about our prediction, being perfect about our forecasting, being perfect about what we are trying to achieve. So in C part, you need to calculate the probability of this false signal happening, because there's always margin of error. There's always margin of error. And we are trying to quantify it. If there's a margin of error, can we try to quantify that number? Can we try to assign some number? Can we try to know the probability of the false signal happening? Yes, exactly. We can. And if what is the formula for the limits for the X bar chart? It is X bar plus minus three standard deviations away from the mean. This is exactly the formula for this, right? So if we have this chart, this is our mu, this is our lower control limit, and this is our upper control limit. And we're saying we're fine if we are within this range, the range shaded within with the red lines. Either we are like below lower control limit or like in this range, right? This is our boundary, the lower control limit and the upper control limit. If we are going above here and here, this is this is the area in which you will signal that your process is out of control. So we need to find the probability of this area. And what would be the probability of this area? The probability of this area would be beyond three standard deviation away, right? This is our z score. Technically, this is our z score. We don't have to find the z score for this example, for the C part. Whenever you're calculating the the probability of the false signal, the z score is automatically being given to you, and which is 3. But you would calculate this z-score on the both sides of the mean, to the left of it and to the right of it. So what you can do is you can go to the z-table and you can only check the probability against 3.00, and whatever that probability is, you can take that probability, right? You can take that probability, sorry, should you can take that probability from 1, right? This would be right? So you can take that probability from 1 and you will get your answer. But that won't be your answer. You will multiply it by 2, because this is a symmetrical distribution. Whatever the area this yellow is, the equal area is on the left, or on the left side. So to find the both areas, because if your sample lies in either to the right of it or to the left yellow shaded region, that would be considered as out of control. So you would add, or you can multiply it by 2, like, right? Or otherwise you can like calculate the value for this or for this separately, but both answers are going to be same, because it's a symmetrical distribution on the both sides of the mu mean. The area is same. So you are 3 standard deviation to the right and 3 standard deviation to the left of it. So it doesn't matter if you just find one and you can multiply it by 2. So I'll share the z chart with you, z table PDF, because it's really important to, and if you just look at the negative value, in that case it will give you the direct, answer, the right answer. Like if you just take the value of minus 3.0, it would give you, I'll I'll show it to you. I'm just making sure that you don't confuse with. Yes. So here you see, if you're looking at the right side, if you're looking at the right side, so you're basically doing this, right? So in this case, you, you to get the right answer, you will take this 0.9987 away from 1 in case you're looking at the positive side. So you would get what? 1 minus 0.9987, you would get 0.0013. This would be the exact answer if you would have looked in the negative side, right? So because your z-score is actually 3.00. So 3.00, this column, right? So you can do like you can get to the right answer in two ways. Either you can do this, and then you will multiply it by 2, and you would get your answer as 0.0026. So it's approximately 0.27 percentage. And similarly, in this case, you would have like you in this case, if you're looking at the negative 3.0, you don't have to like subtract it from 1. It would be your right answer. And this is like there is no science or like technicalities in here. You're just like look at this chart. So basically we're trying to be here on this side or on this side. So it's just like a matter of the notations and direction. It has nothing to do with like some critical like some other formulas or something else. It just has to be it's related to the direction of the area in which direction you are trying to move. So if you're looking at the positive 3 standard deviation, you will take the value away from 1, and if you're looking at the left side, you will take the value as it is. But that would be negative case, and this is positive side, because to the right of the mean it's positive values, and to the left of it are the negative values. And I don't want to go into the details of it because it might be confusing. So I'm just like staying here because I know in your exam, from the exam point of view, you will get like you won't be asked, or so this is all you would have to know to solve the question. So I'm not really going into the depth of that. So this is so 27.27% is basically the probability of the false signal, right? So this is the answer for the C part. And let's move to the D part. Suppose that due to a new inexperienced baker, the mean diameter decreased to 29.8 centimeter, and the standard deviation increases to zero point 0.9. So here you see, there's a difference. If you Let's move to the F part first. In the context of quality control, what is meant by chances causes by variation and assignable cause of variation? So we're talking about two types of causes of changes. Causes of variation and causes of changes are the same thing. And when we started this chapter of statistical process control, we discussed about two types of changes. The one type of change is pure random, something that we cannot understand. the human mind the human mind calls any process, any phenomena that a human mind cannot comprehend, they call it or they refer it as a random, right? So chances, causes of variation, you can think of it as a random changes, something that a human mind or you cannot capture. So you disregard this, right? And here you see, you always keep a margin of error. You always keep a probability of false signal. That's what you're actually doing. You're trying to quantify. You're giving the space for the random changes, right? So that 5% change, like if you have a significance level of like 95, confidence level of 95%, and you're giving away the rest of the 5%, you're actually trying to give space for the random changes. So that's what you're actually doing. But then you also have assignable causes of variation. So this is what we're trying to scrutinize. This is what we're trying to assess. This is what we're trying to keep track of. And if you go back to your D part, now this new inexperienced baker is basically your assignable cause of variation. Like you put the inexperienced person on work. So the changes, the decrease in the mean, the change in the standard deviation is due to the human error who is inexperienced. So this is assignable cause of variation. This is not a random cause of variation because this is something we can understand, right? So this is what the difference between the chance causes of variation and assignable causes of variation. Now let's do and calculate. So let's do the maths in the deep part. Suppose our mean has went down to 29.8 and my standard deviation is I think is increased to zero point 0.9 centimeter. How many samples on average would be taken before this an assignable cause of variation is signaled by the X bar? Here you have to answer the number of samples. The number of samples that it takes on average before it signals out this assignable cause of variation. Right? We have a process in place and I know that there's been change in the process. My mean is changed, my standard deviation changed, but I am trying. So I, although as a human, I know, as a manager, I already know, but I want to assess the quality of my system, statistical process control. I want to assess the quality of my statistical process control, which I have put in place to whose complete job is to identify if there is any major change in the process, if there's any major change in the mean and in the parameters of this whole process. So how many samples it would take? I we have a way to measure this and we call it ARL. We call it ARL, average run length, I believe. This is what we mean. And what is the formula to find this? To find this ARL, I need the probability, right? Because the formula for this is one upon p for the ARL. The probability of what? The probability of the sample getting signaled out, right? So I need to find this. And how we used to find that value? I have my upper control limit, which was what? For the X bar chart, right? Because we're talking about X bar chart. What was the upper control limit for the X bar chart, if you remember? Hmm? What was it was 30.1. My UCL for the X bar chart was 30.1. And my lower control limit was 29.3, 29.3. My LCL was 29.3. Now I'll have to find the Z score, right? I'll have to find my z-score, and corresponding to z-score, I'll find the probabilities and I'll add those probabilities. By adding the probabilities, I'll get the probability of sample getting signaled out after the assignable cause of variation. And once I have that probability, I can take the reciprocal of the probability to get the number of samples that it would take before it signal out this like assigned cause of variation. So this is like a whole chain or a process. And how I'll find my z-score? My new mean is what? My new mean is 29.8, right? My UCL minus 29.8 divided by standard error. Now, how would I find my standard error? Standard deviation divided by n bar. My standard deviation is changed here. My standard deviation, I'll use the new one, which is zero point 0.9 divided by what was my sample size? 4 under root. So what would be the standard deviation? The standard deviation would be 0.45 centimeter. This is my standard error. And let's find the z-score. 31.1 minus 29.8 divided by 0.45. This would give me the z-score for the UCL. And for the LCL, it would be 29.3. I'm finding the z-score for the LCL. 29.3 minus 29.8, which is my mean, divided by a standard error is 0.45. And let's see what is the z-score for the upper control limit. It's 2.889. And the z-score for the lower control limit, it's minus 1.111. So this is why if you like take it to the three decimal places, that would be minus 1.111, and similarly for the z-score for the UCL. Now for the last time I'm explaining, so this is like, because this is a really good example to just get done with this intuition. I told you, this is your mean, right? This is your UCL, and this is your LCL, let's say. Now, your UCL is how far away your UCL is. This is what the Z-score tells you, 2.889. And how far your LCL is, it's minus 1.111. This positive 2.889 means that UCL is to the right of your mean and LCL is to the left of your mean. So your process will signal out if your any mean falls above UCL or below LCL. Why below LCL? Because this is the negative side of the number line. If this is minus 1 and if this is 1 minus 1 point, let's say 0.1, minus 1.01 is less than minus 1, because on the negative side of the number line, minus 1 would be greater than minus 4, right? So what you do is you will find the probability of Z score if greater than 2.889 plus the probability of Z score less than minus 1.111. Because if Z score is minus 1.111, that means you're in this yellow shaded region, your point is in this yellow shaded region, and Z greater than 2.889 means any point who is above this Z score, and that would be the point which lies to the right side, the yellow shaded region on the right side of the graph. So this is what it means. Now go to the Z table and look for these values. And I'm not sure if I have the values over here. 2.899. I have 2.8. Yeah, I'll have to go to the table, by the way. And for this, you will subtract it from minus 1, by the way. And for this, you don't have to subtract it from minus 1. So for this, the probability for the UCL, it's 0.00194 plus for the LCL, it is 0.1333. So this is coming from the UCL. And for the LCL, this is the probability. And you will add those up. You will add those up to get the complete probability. And that would be 0.1352 by adding these numbers. So this is your probability. 13.52 is the probability, right? In terms of percentage, 13.52 percentage. So this is your probability. And to find the ARL, what would you do? You'll take the reciprocal of 0.1352. You'll get the number. And what is that number? 7.4, right? So 7.4 samples would be taken before, on average, if I have to interpret this, I'm writing the interpretation on average, approximately 7.4 samples would be taken before the cause assigned cause is detected. And what was our assigned cause? Our assigned cause was the appointment of an inexperienced person, right? So that was our assigned cause. I hope this makes sense. And our last part E, how often should samples be taken to ensure that the assignable cause of variation described in part E would be signaled? So this is not part E, but part D. This is what they mean. This is the question of the, and we so question E says that we want to signal out that cause of variation within 6 hours. So this is the ATS. They have given us the ATS. They want to detect this cause of variation, this assigned cause of variation within the 6 hours, right? And this is exactly how we define the average time to signal. Our average time to signal is the time taken to signal out the cause of variation. So they have given us the ATS, but what they wanted to ask, they want to ask how often should we take the sample in order to signal out the cause of variation within 6 hours, right? So let's do this, right? Our ATS given to us is 6 hours. We know my ARL is how much? 7.4. My ARL is 7.4, 7.4. And I want to know how often I should be taking sample. How often I should be taking sample. Do we have a formula to find this? Yes, exactly. What is the formula for the ATS? The formula for the ATS is ARL multiply by the sample taken time. So like this means how much time, after how much time I'm taking each sample, right? And I need to find out this. So my ATS divided by ARL would give me this answer. So if your ATS is 6 hours and your ARL is 7.4, if you divide them, you will get STT, the sample time taken. And that would be, and you will get 0.81 hours because we are dealing in the hours, 6 hours. So this 0.81 is your answer, right? And you can convert it into minutes. That would be approximately 49 minutes. And how would you divide, how would you get the minutes? If you multiply this hour by 60, you will get 49 minutes. So you must be taking sample after 49 minutes in order to, detect this cause of variation within next 6 hours. So this is the complete example. Now we get done with the statistical process control, and I hope it does make sense. Thank you so much.